Every single complex technical project operates under a harsh mathematical certainty. It will inevitably deviate from its original plan. We measure this deviation against the triple constraint. This is the rigid baseline of any project, formed by its defined scope, cost, and time. As execution begins, external variables continuously strike this baseline. Every impact introduces variance, forcing the schedule or budget to warp. In project management, we define this mathematical uncertainty strictly as risk. It is distinct from an issue. An issue is a known problem currently affecting the project. A risk is an event that has not yet happened. Novice managers treat risk as a synonym for danger. They focus entirely on what might go wrong. But statistical variance swings in both directions. Risk encompasses negative threats, like supply chain delays, and positive opportunities, like a sudden drop in material costs. Managing a project requires building a quantitative architecture. This system captures positive opportunities while actively truncating negative threats. You cannot manage chaotic variables until you systematically identify and categorize them. To scan for external variables, we use PESTLE. PESTLE categorizes environmental factors into political, economic, social, technological, legal, and environmental groups. By filtering the environment, we detect macro-level shifts, like economic tariffs or tech upgrades, that remain outside the project manager's control. Once the external environment is scanned, the focus shifts inward to uncover internal project dependencies and single points of failure. This is a fishbone diagram. We use it to trace a potential internal failure back to its origins. Mapping variables backward reveals hidden root vulnerabilities. Before a failure triggers, you discover that a reliance on a single supplier is structurally compromising your timeline. Applying these frameworks converts invisible, hypothetical events into a documented physical inventory of potential variances. With a complete inventory of potential variances, a new problem emerges. Human intuition is terrible at accurately assessing raw probability. Project resources are finite. You cannot allocate capital and time to mitigate every item on the list. You need a rigorous triage system. This chart is a probability impact matrix. We use it to calculate an inherent risk rating for each identified variable. The matrix evaluates two core components. Probability measures the mathematical likelihood that an event will occur. Impact measures the exact magnitude of the effect on the project baseline. Combining these generates a standardized overall risk score. By plotting raw data points onto this grid, we visually segregate minor background noise from the critical threats. The low probability, low impact events cluster at the bottom, isolating the severe threats in the top right quadrant. Any variable landing in this high probability, high impact zone requires immediate escalation. We must move away from qualitative guessing and apply quantitative mathematical rigor. For top-tier risks, qualitative labels like high or medium are insufficient. We need hard mathematical data. Consider a scenario where a project faces a major strategic choice under uncertainty, such as choosing how to scale a new software architecture. This decision tree maps costs and probabilities to distinct pathways, comparing a $500,000 marketing campaign against a $200,000 sponsorship strategy.
On the first pathway, we split the branch to reflect a 60% probability of strong demand and 40% weak demand. We map the competing pathway the same way, with its lower upfront cost and different demand probabilities. At the end of each branch, we calculate the expected monetary value. The math proves that the cheaper $200,000 pathway actually yields a better risk-adjusted return. To map the entire probability space for complex projects, we use Monte Carlo simulations. A Monte Carlo simulation is a computational algorithm that relies on repeated random sampling to predict the probability of thousands of different scenarios. These quantitative tools remove human emotion from complex project forks. They prove mathematically which path optimizes capital against uncertainty. Massive infrastructure or technical projects contain dozens of shifting variables interacting simultaneously. We need to know which single variable has the power to cause the most extreme deviation to the budget or the schedule. We isolate individual variables and measure their specific impact using sensitivity analysis. This tornado chart visualizes sensitivity by ranking variables by their magnitude of impact, placing the most volatile factor at the top. On the top bar, adjusting commission percentages drastically swings project revenue, pushing the entire project from a profit into a $200,000 loss. Sensitivity analysis shows the project manager exactly where to focus their risk mitigation budget to protect the baseline. With the math solved, risk response is no longer reactive troubleshooting. It is deliberate, strategic allocation. We handle negative risks, or threats, using 4 distinct response vectors. We can avoid the risk by eliminating the pathway entirely. We can mitigate it by reducing its probability or impact. We can transfer the financial burden to a third party, or we can accept it, allocating a reserve to absorb the hit. Positive risks, or opportunities, require their own equivalent vectors. Amateurs normally ignore these, leaving value on the table. To capture an opportunity, we can exploit it to guarantee it happens. We can enhance it to increase its probability, or we can share the opportunity, partnering to capture value. Applying these explicit vectors results in a controlled, engineered project environment. The output of this entire analytical engine must live in a central nervous system, the risk register. The risk register is a dynamic, probabilistic governance interface. It catalogs every identified variance, its calculated EMV, and its assigned response vector. As the project lifecycle advances and new data arrives, the matrix, models, and vectors within the register must continuously iterate. Risk profiles degrade and evolve over time. An unmonitored risk plan becomes a useless artifact almost immediately. Project leadership is defined by the navigation of variables, rather than the accuracy of a rigid schedule. Ultimately, true project leadership is the active mastery of risk-based decision-making in the face of absolute uncertainty. By rigorously quantifying the unknown, a manager gains the strategic advantage to capture unseen value and guarantee execution.